In electrical engineering, a protective relay is a device designed to trip a circuit breaker when a fault is detected. The first protective relays were electromagnetic devices, relying on coils operating on moving parts to provide detection of abnormal operating conditions such as overcurrent, overvoltage, reverse power flow, over and under frequency. Microprocessor-based digital protection relays now emulate the original devices, as well as providing types of protection and supervision impractical with electromechanical relays. In many cases a single microprocessor relay provides functions that would take two or more electromechanical devices. By combining several functions in one case, numerical relays also save capital cost and maintenance cost over electromechanical relays. However, due to their very long lifespan, tens of thousands of these silent sentinels are still protecting transmission lines and electrical apparatus all over the world. An important transmission line or generator unit will have cubicles dedicated to protection, with many individual electromechanical devices, or one or two microprocessor relays. The theory and application of these protective devices is an important part of the education of an electrical engineer who specializes in power systems. The need to act quickly to protect circuits and equipment as well as the general public often requires protective relays to respond and trip a breaker within a few thousandths of a second. In these cases it is critical that the protective relays are properly maintained and regularly tested. Operation principles: electromechanical protective relays operate by either magnetic attraction, or magnetic induction. Unlike switching-type electromechanical relays with fixed and usually ill-defined operating voltage thresholds and operating times, protective relays have well-established, selectable and adjustable time-current operating characteristics. Protection relays may use arrays of induction disks, shaded pole magnets, operating and restraint coils, solenoid-type operators, telephone relay contacts, and phase-shifting networks. Protective relays can also be classified by the type of measurement they make. A protective relay may respond to the magnitude of a quantity such as voltage or current. Induction types of relay can respond to the product of two quantities in two field coils, which could for example represent the power in a circuit. Although in electromechanical relay calculating the ratio of two quantities is not practical, the same effect can be obtained by a balance between two operating coils, which can be arranged to effectively give the same result. Several operating coils can be used to provide bias to the relay, allowing the sensitivity of response in one circuit to be controlled by another. Various combinations of operate torque and restraint torque can be produced in the relay. By use of a permanent magnet in the magnetic circuit, a relay can be made to respond to current in one direction differently from in another. Such polarized relays are used on direct current circuits to detect, for example, reverse current into a generator. These relays can be made bistable, maintaining a contact closed with no coil current and requiring reverse current to reset. For AC circuits, the principle is extended with a polarizing winding connected to a reference voltage source. Lightweight contacts make for sensitive relays that operate quickly, but small contacts can't carry or break heavy currents. Often the measuring relay will trigger auxiliary telephone-type armature relays. In a large installation of electromechanical relays, it would be difficult to determine which device originated the signal that tripped the circuit. This information is useful to operating personnel to determine the likely cause of the fault and to prevent its reoccurrence. Relays may be fitted with a target, or flag unit, which is released when the relay operates, to display a distinctive colored signal when the relay has tripped. Types according to construction: electromechanical relays can be classified into several different types as follows. Armature-type relays have a pivoted lever supported on a hinge or knife-edge pivot, which carries a moving contact. These relays may work on either alternating or direct current, but for alternating current, a shading coil on the pole is used to maintain contact force throughout the alternating current cycle. Because the air gap between the fixed coil and the moving armature becomes much smaller when the relay has operated, the current required to maintain the relay closed is much smaller than the current to first operate it. The returning ratio, or differential is the measure of how much the current must be reduced to reset the relay. A variant application of the attraction principle is the plunger type or solenoid operator. A reed relay is another example of the attraction principle. Moving coil meters use a loop of wire turns in a stationary magnet, similar to a galvanometer but with a contact lever instead of a pointer. These can be made with very high sensitivity. Another type of moving coil suspends the coil from two conductive ligaments, allowing very long travel of the coil. Induction disk overcurrent relay. Induction disk meters work by inducing currents in a disk that is free to rotate. The rotary motion of the disk operates a contact. Induction relays require alternating current. If two or more coils are used, they must be at the same frequency, otherwise no net operating force is produced. These electromagnetic relays use the induction principle discovered by Galileo Ferraris in the late 19th century. The magnetic system in induction disk overcurrent relays is designed to detect overcurrents in a power system and operate with a predetermined time delay when certain overcurrent limits have been reached. In order to operate, the magnetic system in the relays produces torque that acts on a metal disk to make contact, according to the following basic current torque equation, where a is a constant and the two fluxes is the phase angle between the fluxes. The relay's primary winding is supplied from the power system's current transformer via a plug bridge, which is called the plug setting multiplier. Usually 7 equally spaced tappings or operating bands determine the relay's sensitivity. The primary winding is located on the upper electromagnet. The secondary winding has connections on the upper electromagnet that are energized from the primary winding and connected to the lower electromagnet. Once the upper and lower electromagnets are energized, they produce eddy currents that are induced onto the metal disk and flow through the flux paths. This relationship of eddy currents and fluxes creates torque proportional to the input current of the primary winding, due to the two flux paths being out of phase by 90 degrees. In an overcurrent condition, a value of current will be reached that overcomes the control spring pressure on the spindle and the braking magnet, causing the metal disk to rotate towards the fixed contact. This initial movement of the disk is also held off to a critical positive value of current by small slots that are often cut into the side of the disk. The time taken for rotation to make the contacts is not only dependent on current but also the spindle backstop position, known as the time multiplier. The time multiplier is divided into 10 linear divisions of the full rotation time. Providing the relay is free from dirt, the metal disk and a spindle with its contact will reach the fixed contact, thus sending a signal to trip and isolate the circuit, within its design time and current specifications. Drop-off current of the relay is much lower than its operating value, and once reached the relay will be reset in a reverse motion by the pressure of the control spring governed by the braking magnet. Static application of electronic amplifiers to protective relays was described as early as 1928. Using vacuum tube amplifiers. Devices using electron tubes were studied but never applied as commercial products, because of the limitations of vacuum tube amplifiers. A relatively large standby current is required to maintain the tube filament temperature. Inconvenient high voltages are required for the circuits, and vacuum tube amplifiers had difficulty with incorrect operation due to noise disturbances. Static relays with no or few moving parts became practical with the introduction of the transistor. Static relays offer the advantage of higher sensitivity than purely electromechanical relays, because power to operate output contacts is derived from a separate supply, not from the signal circuits. Static relays eliminated or reduced contact bounce, and could provide fast operation, long life and low maintenance. Digital. The functions of electromechanical protection systems are now being replaced by microprocessor-based digital protective relays, sometimes called numeric relays. These convert voltage and currents to digital form and process the resulting measurements using a microprocessor. The digital relay can emulate functions of many discrete electromechanical relays in one device, simplifying protection design and maintenance. Each digital relay can run self-test routines to confirm its readiness and alarm if a fault is detected. Numeric relays can also provide functions such as communications interface, monitoring of contact inputs, metering, waveform analysis, and other useful features. Digital relays can, for example, store two sets of protection parameters, which allows the behavior of the relay to be changed during maintenance of attached equipment. Digital relays also can provide protection strategies impossible to synthesize with electromechanical relays, and offer benefits in self-testing and communication to supervisory control systems. Numerical. The distinction between digital and numerical relay rests on points of fine technical detail, and is rarely found in areas other than protection. They can be viewed as natural developments of digital relays as a result of advances in technology. Typically, they use a specialized digital signal processor as the computational hardware, together with the associated software tools. The input analog signals are converted into a digital representation and processed according to the appropriate mathematical algorithm. Processing is carried out using a specialized microprocessor that is optimized for signal processing applications, known as a digital signal processor or DSP for short. Digital processing of signals in real time requires a very high-power microprocessor. Relays by functions. The various protective functions available on a given relay are denoted by standard ANSI device numbers. For example, a relay including function 51 would be a timed overcurrent protective relay. Overcurrent relay. A digital overcurrent relay is a type of protective relay which operates when the load current exceeds a preset value. The ANSI device number is 50 for an instantaneous overcurrent and 51 for a time overcurrent. In a typical application, the overcurrent relay is connected to a current transformer and calibrated to operate at or above a specific current level. When the relay operates, one or more contacts will operate and energize to trip a circuit breaker. Distance relay. The most common form of protection on high-voltage transmission systems is distance relay protection. Power lines have set impedance per kilometer, and using this value and comparing voltage and current, the distance to a fault can be determined. The ANSI standard device number for a distance relay is 21. It is also called as the impedance relay as it calculates the line fault with the use of the impedance per meter of the transmission line. There are many types of distance relays including impedance distance, reactance distance, offset distance and mode distance. Current differential protection. Another common form of protection for apparatus such as transformers, generators, buses and power lines is current differential. This type of protection works on the basic theory of Kirchhoff's current law, which states that the sum of the currents entering and exiting a node will equal zero. Differential protection requires a set of current transformers at each end of the power line, or each side of the transformer. The current protection relay then compares the currents and calculates the difference between the two. As an example, a power line from one substation to another will have a current differential relay at both substations which communicate with each other. In a healthy condition, the relay at substation A may read 500 amps and substation B will read 500 amps. If a path to earth or ground develops, there will be a surge of current. As supply grids are generally well interconnected, the fault in the previous example will be fed from both ends of the power line. The relay at substation A will see a massive increase in current and will continue to export. Substation B will also see a massive increase in current, however it will now start to export as well. In turn, the protection relay will see the currents traveling in opposite directions, and instead of cancelling each other out to give a summation of zero, it will see a large value of current. The relays will trip the associated circuit breakers. This type of protection is called unit protection, as it only protects what is between the current transformers. Often, differential protection relays will have a rising characteristic to make the operating set point a function of the through current. The higher the current in the line, the larger the differential current required for the relay to detect as a fault. This is required due to the mismatches in current transformers. Small errors will increase as current increases to the point where the error could cause a false trip, if the current differential relay only had an upper limit instead of a rising differential characteristic. Current transformers have a point where the core saturates and the current in the CT is no longer proportional to the current in the line. A CT can become inaccurate or even saturate because of a fault outside of its protected zone where the CTs see a large magnitude but still in the same direction. Directional relay. A directional relay uses an additional polarizing source of voltage or current to determine the direction of a fault. The fault can be located upstream or downstream of the relay's location, allowing appropriate protective devices to be operated inside or outside of the zone of protection. Synchronism check. A synchronism checking relay provides a contact closure when the frequency and phase of two sources are similar to within some tolerance margin. A sync check relay is often applied where two power systems are interconnected, such as at a switch yard connecting two power grids, or at a generator circuit breaker to ensure the generator is synchronized to the system before connecting it. References: ABC Protective Relays Application Guide 3rd edition, GEC Alstom Measurements Limited 1987, No ISBN, pages 9-10, 83-93, T.S. Madhava Rao, Power System Protection, Static Relays with Microprocessor Applications, Tata McGraw-Hill, 1989, ISBN 0-07-460307-8, pages 1-2, Li Tan and Jean Jiang, Digital Signal Processing, Fundamentals and Applications, Academic Press. 2nd edition, 2013, ISBN 0-12-415893-5, pages 405-452, Elmore 2003, PA 247. C. Russell Mason, The Art and Science of Protective Relaying, General Electric, available at 1, Elmore, W.A. Protective Relaying, Theory and Applications. Taylor and Francis. ISBN A9780824709709,723. Retrieved January 17, 2014. A.